Hello everyone! For this tutorial video, I like to transition away from the study of prisms and pyramids, and toward the study of 3D shapes made out of polygons that are too complicated for either category. You may hear, just like any 2D shape made out of straight lines is called a polygon, a 3D shape whose faces are all polygons, no curves, is called a polyhedron, and has a very similar etymology to polygon, where polygon means poly many and gon angles from ancient Greek, and polyhedron means poly many and hedron face, also from ancient Greek. Just like there's a special type of class for pyramids and prisms called regular pyramids and prisms, there is also a special type of class for more complicated polyhedrons called regular polyhedrons, and the strict definition of these is very similar to regular polygons for 2D geometry. In particular, a regular polyhedron is defined as a polyhedron whose faces are only regular polygons. And generally, because of the way 3D shapes are made out of folding 2D shapes, if all the faces are regular, it would have to follow that all the faces are equal to each other as well, in terms of their surface area. Because of this convenient fact, we can simply multiply the number of faces times the area of one of the faces to get the total surface area, without having to decompose the shape. However, it would still be best practice to decompose the shape anyway, in order to understand how the shape is made, both in real life and in software applications. A polyhedron that looks a little bit like a crystal, like this, can be broken down into two pyramids with one prism between them, because of how the bases of the pyramids match the bases of the prism in terms of area. Therefore, the volume would be a simple summation of these dissected parts. However, the surface area is more complex, because of how the bases of the prism and pyramids are on the inside of the shape and therefore not part of the surface area. So you cannot simply add the surface area of each individual section, much like the problem we ran into finding the perimeter of an irregular polygon. However, what we can do is add the surface area of the individual sections and subtract the area of all of these bases, which are only two in this case. So even though the object is much more difficult to unfold than a prism or pyramid, the surface area can be found by breaking it down into shapes that do have an easy to find surface area visually, and then simply adding and subtracting the areas as appropriate. However, not every regular polyhedron will be this easy to split apart, because sometimes you will have to do some work to break down the shape into perfect pyramids and prisms. For example, this shape that looks like a hexagonal ball has no prisms constituting its volume, as the cross-sectional area is always changing, but it also appears at first glance not to have any pyramids either, as the ends do not taper off into a triangular tip. However, we can see these ends are nothing more than sections of pyramids, and the bases of these two pyramids would meet in the middle. So once we complete the pyramids on either side, and then multiply the height by the appropriate percentage, we can figure out the overall volume of this shape. The surface area would be calculated in basically the same way, making sure to carry out the appropriate step of subtracting the base in the middle, where the two pyramid sections meet. Luckily for us, the surface area of this particular shape is pretty convenient to visualize, owing to the fact that it is based off of 2 times the surface area of a shape we already know. So if we were to flatten out the shape, we could see it was simply a pentagon at either end, with 5 pentagons surrounding each, and the pattern would be arranged in a way so that one would be the top of the shape and the other would be the bottom. However, there are some regular polyhedrons that manage to be extremely difficult, all while still remaining regular. For example, this polyhedron that looks like a spiked ball looks very, very daunting at first, compared to the more simpler shapes of the other two, but can be seen as a complex sum of many pyramids. So the volume would simply be an addition of all of these pyramids, which we would have to stop and count. And the surface area would be the surface area of all the pyramids, minus all the bases of the pyramids, because of how in this case all the bases are on the inside of the shape. So even though the 2D representation of the overall surface area would be very messy, we can divide it into sections, where each section would add up to the surface area of a pyramid, without the base. Now that I've explained how to break down sophisticated regular polyhedrons into simpler polyhedrons, I can explain how to break down sophisticated irregular polyhedrons into simpler shapes, which uses the same exact techniques. It's just that the surface area has to be found manually now, as the faces are no longer all equal to each other. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.